Hello and welcome to the presentation on on-site Gamma-Hadron Separation with deep learning on FPGAs here at ECML-PKDD 2020. My name is Sebastian Buschjäger and I'm part of the Artificial Intelligence Research Group here in Dortmund. And together with my colleagues Lukas Pfahler, Jens Bus, Katharina Morik, and Wolfgang Rode, I'm happy to share our work on this topic. Before diving into it, let me give you a quick recap about Gammaray Astronomy. So, in order to understand our universe, you have to observe it. And one way to do so is to observe the particle interactions in the Earth's atmosphere. So, for example, a supernova is happening somewhere in the universe, then those energy beams transmitted by it would at some point eventually hit the Earth's atmosphere. There, they begin to interact with particles in the atmosphere, which leads to a chain reaction of more and more interactions with different particles, and particles start to interact with each other, stuff like that. And eventually, this cascading air shower produces what's called Cherenkov light. And in turn, this Cherenkov light can be captured by a telescope. Now, those measurements need to be processed in rather lengthy processing pipelines to finally show an image like this, where we have the telescope surface, and here we have an air shower hitting it. Just to give you a little bit more context about this approach or this project we work in, we work together with the FAC telescope. That's the first G-APD Cherenkov Telescope. It produces roughly 180 megabytes of data per second, or differently put, roughly 60 events per second happened. Of those, only 1 in 10,000 measurements are actually interesting. The remaining measurements are due to the ever-present background noise of the universe. And in order to get the best view, we would put such a telescope on a remote mountain on, let's say, La Palma in this case. So the bandwidth, the computational power, as well as the physical space is limited. So at some point, somebody has to take all the equipment, put it in a truck, drive it up there, and build the telescope. So you want to minimize the equipment you need. So what's the processing pipeline here? First, the data gets calibrated to account for any environmental changes, such as day-night cycle, changes in temperature. Then some basic image cleaning is performed because over the years, a couple of sensors broke, for example. And then we perform a feature extraction of up to 80 different high-level features, which have been designed by physicists and domain experts. And those high-level features are then being used to perform the signal noise separation. So we would decide if an event is interesting or uninteresting. If it's interesting, we would like to know where to look. So where happened this event in the universe? So we need to reconstruct its origin. And in order to reason about it from a physics point of view, we would need to have the energy of the event. In this paper, we focused on the signal separation task because it's one of the most difficult tasks and because physicists already use a machine learning model here. So more specifically, they deployed random forest using the high-level features. And so we have a baseline to compare against. And we asked in this paper, our goal was to replace this rather lengthy processing pipeline with a single machine learning model. And we proposed to do so using deep learning methods. So we used simulation data and used the same rock data calibration which we use on site at the telescope, and then did deep learning on that. Came up with a tool to deploy those deep learning models in a rather efficient way, so we can just put them directly at the telescope. So this is the outline. I'm going to walk you through each of those steps. So let's start with the data simulation and data calibration. So in astrophysics, it's usually difficult to obtain labeled real-world data. So pretty much the particle or energy beam from out of space doesn't come with a label. However, physicists know pretty well how particles interact with each other and how the Earth's atmosphere is composed and what might happen there from a physical point of view. So we can build a pretty accurate simulation, and that's what we used here. Also, the Corsica simulation is exactly such a simulation software. Depending on the parameters for the simulation, they sometimes work better, sometimes they don't work well. So what the physicists came up with are what we would call quality cuts. So they would decide the simulation looks good, seems to be close to what would happen in the real world, and the simulation doesn't look as good, so this might be due to some weird simulation effects. So we rather not use those. So we have two types of data sets, one with these quality cuts and one without. In total, we have 200,000 training data points, 100,000 test data points, And for these experiments, we used an equal distribution, so 50% background, 50% due to something interesting. And this just helps the general machine learning approach in the end. So for preprocessing, we performed minimal preprocessing, and basically the reference voltage curves of a single photon hitting a single sensor are known. So we know how it looks like if a single photon hits a single sensor over a 300 nanosecond time period. And what we can do is we use this reference curves and subtract it as often as possible from the actual measurements. And this way we can roughly estimate the number of photons hitting a single sensor of the telescope surface in a given period of time. And the result of this is a 45 times 45 image where each pixel contains the number of photons hitting the telescope surface in a given time period. Just to give you a quick example, here on the left side we have the classical air shower, so to speak, and here on the right side we have the resulting images. So in green, that's the telescope surface. This is usually a hexagonal grid, but we transformed it to fit into this Euclidean grid for the image processing. The red part here, that would be padding pixels. They are never used, always 0. And the blue part here, that's the actual shower hitting the telescope. Now let's look at the machine learning part. Well, the general approach is for us was to start simple and gradually increase the complexity. And just to make it clear, our training data were these 45 times 45 images with integer values in each pixel, and the labels were either 0 or 1, so background noise, something interesting. In total, we performed 1,178 experiments, and in general, we found that smaller models work better. We had some success with early stopping and learning rate scheduling. We also tried ResNets, and they improved the performance, but weren't really justified due to the longer training times. So in the end, we settled for a simple VGG-like architecture, the 3x3 convolution, followed by batch norm ReLU into max pool, and this block is repeated a couple of times, and then in the end, fully connected is used for the final classification. As I mentioned, we're in a very resource-constrained environment here, and so we also looked into more resource-efficient versions of deep learning, and arguably one of the most extreme versions are binary neural networks, because they use weights which are either -1 or +1 instead of the whole range of floating point numbers available. This makes training a little bit more difficult. We would need to use something like deterministic binarization in combination with the full precision stochastic gradient descent. I'm not going to go into details about this here because it would take too much time. But why are they so great for fast inference on small devices? Well, first of all, they need 30 times less memory than what a regular floating point network would use. So because we can use a single bit to store a single weight, and then we can process a bunch of weights in only 2 clock cycles. So let's say we have -1 or +1, so we will map those to Boolean values. So -1 gets mapped to 0, +1 gets mapped to 1. Then the multiplication here is pretty much the XOR operation. And then the sum over those multiplications is counting the number of ones and zeros in the resulting bit string. And in computer architecture, there is a instruction for that called pop count. For example, Intel CPUs usually ship with those, and some ARM CPUs also ship with those. So we can process a pack of 128 bits, for example, in 2 clock cycles by using XOR and pop count. This is why these types of networks are so interesting. Then we looked at how to utilize those special types of networks, and there are a couple of inference engines out there which perform a very efficient forward pass for deep learning models. However, we couldn't find any utilizing those special structure of binarized neural networks, so having +1 or -1 and using pop count and XOR efficiently. So we came with our own solution, and just to quickly give you an overview, the basic idea is to take the model and unroll it into its entire C code. So just read it and generate the code and all the weights into one file. And so to do so, we would read the file, maybe perform some post-training optimization, which we didn't use here. Then we would choose a target architecture, for example, an Intel, ARM, or FPGA. And so in Intel, we would replace a placeholder for pub count with the specific Intel instruction. And similarly on ARM and on an FPGA, we would provide our own implementation for pub count. And then we would just choose from a set of different templates we have pre-programmed and replace the appropriate placeholder in those templates. So if we have a binary convolution, then we would use that and replace the pub count as we would need to. So for our experimental analysis, we had 3 questions. First, do CNNs and binary CNNs outperform random forest on using high-level features on the simulation data? Second, how does it look like in the real world? So we know that random forest generalize pretty well in this context, and we weren't sure if CNNs and binary CNNs would do the same. And then last, is the implementation we provided really real-time capable? So let's look at the first experiment. We see that the random forest using the high-level features, that's called data level 2 here, roughly is in the range of either 70% accuracy or 78% accuracy. Random forest trained on the photon count data, so that's what I've shown you with the reference curves, improves the performance slightly. But if we look at the deep learning approaches, they all outperform the random forest approaches by quite a margin. So we would expect something in the range of 90% accuracy to 94%. So that's a win for the deep learning method here. Now looking at the real-world data, we used the Crab Nebula data, and what the physicists did is they designed a statistical test and will measure the performance in terms of sigma values to reject the null hypothesis. So for the baseline, we are in the range of 22 to 23, 24-ish sigma values. And so the photon count stream data combined with the random forest shows severe overfitting. So the sigma values here are very, very bad. Now looking at the deep learning approaches, we see some which are worse, some which are on par with the random forest, and some which even outperform those. So and if we perform a good model selection using those 2 models, for example, we would improve the performance. So we have improved performance on the simulation data as well as in the real world data. So another question is this whole approach real-time capable? We compared against Onyx runtime. This is a runtime engine from Microsoft optimized towards the more traditional floating point networks, and we see that we're in the range of 21 milliseconds to 1 millisecond. So this 21 milliseconds would be too slow to keep up with the data rate of the FACT telescope, whereas 1 millisecond is quick enough. So our goal is to roughly reach 16 milliseconds. Looking at the generated code, the floating point networks are pretty slow because we didn't optimize any of this code. But looking at the binary code, we see that we get actually quicker, and we are quicker than the Onyx runtime in this case, which is pretty cool. However, we also have to note that the small binarized neural network here is slower than the floating point network. This is probably due to the fact that those experiments have been run on an Intel machine, which are more optimized towards floating point operations. We double-checked this implementation, or we used this implementation as a starting point for FPGA design, and we came up with a pipeline solution which offers even better performance. And this is really just the first step. We didn't do any optimizations over a longer period of time here. So if we would take a couple of weeks to optimize it further, we would expect to increase the performance here. So just quick recap of what I showed you today. So Gammaray Astronomy uses these lengthy processing pipelines, and currently a random forest is used for signal separation using high-level features, and we try to replace this with a single model using deep learning and a combination of code generation to come up with a fast implementation. And we have excellent performance on training data, and improved performance on real-world data. The whole implementation is real-time capable, so we could use a small ARM processor to run the inference directly at the site, so directly at the telescope. And if necessary, we could also come up with a better FPGA implementation to further increase the performance. Thank you, and I hope to see you in the Q&A session.